So we're going to start in section 8.1, which is just about two-dimensional vectors. So a vector is a fundamentally different type of mathematical quantity than we're used to working with. So a vector quantity has two components to it. It has a magnitude and it has a direction. So there's lots of different ways that we can represent a vector. One of them is kind of geometrically. So we can draw an arrow pointing in some direction, and this can represent a vector. The length of this arrow is the magnitude, and the direction which it points is the direction. So the direction is just wherever it's pointing. So for example, in first semester, we talked about some vector story problems, right? You guys kind of remember doing that. So maybe we had a wind, let's say a 30 mile per hour wind blows in the, I don't know, at a bearing, I think that was the vocab we used, of, 167 degrees or something, right? This is describing one thing. It's describing just one vector. Again, a vector has two quantities. It has a magnitude, and then it has a direction, which tells you kind of where that force is being applied or where that magnitude is being applied. And in first semester, when we did these vector story problems, we dealt with vectors that were described only in this fashion as magnitudes and directions, right? What we're going to do here straight away is introduce another representation of a vector. So when we talk about a vector in component form, the notation that we're going to use to represent that is we're going to use these wedge-shaped brackets. And the component form for a two-dimensional vector just has two components to it. It's a comma b. And what this component form is representing is it's a vector where the tail of my vector, if I'm drawing an arrow, there's a tail and a head. The tail of the vector is at the origin, and the head of the vector is at the point AB. So for example, if I wanted to draw the vector -3, 5, that's what I'm going to draw, right? The initial point of my vector is at the origin, and the terminal point of my vector is at the point -3, 5. Is everybody okay with that idea? Okay. Okay. The magnitude, which we denote with the vertical bar notation, is simply the length of the arrow. So probably worth mentioning this here before. So I neglected to do that. Let me mention it now. When I use a variable to represent a vector quantity, I'm going to put that little vector hat on top of it to differentiate a variable that's a scalar quantity that's just like a number versus a variable that's a vector quantity that has a magnitude and a direction associated with it. So V, that's a scalar, that's just like a regular variable. V with the little hat on it is a vector quantity that has a magnitude and a direction to it. So that's just a little piece of notation there. Now, in the text, instead of using this little vector with a hat, we use a boldface letter V. So that's not on accident. So in this chapter in particular, if you're looking at the text, you must be very careful. The boldface letters are vector quantities. The regular typeface letters are variables, just regular scalar quantities. Okay? All right. So the direction of a vector is just the direction the arrow's pointing. We use our standard position angles in the XY plane to describe that vector, or to describe that direction. So if I go back and I look at this vector that I drew just a moment ago, this is my direction then. Typically, I'll use the Greek letter theta to describe a direction, but it's the same standard position angle that we used all throughout first semester. A scalar is just a number. It's not a vector. Like 5 is a scalar. But, you know, magnitude 7, direction 72 degrees is a vector, where you have two parts to it. You have a size and a direction. All right. Suppose we have the vector with initial point at 3, -2, and terminal point at 5, 1. And let's say we want to get this into component form. Let's draw ourselves a picture of what's going on here before we kind of figure out how we're going to be able to do this. So let's see, we have 3, -2, and then I have 5, 1. So that's my vector AB. Notice when I write that vector, the order of the two letters matters quite a bit. Just like in geometry, when you wrote array, the order of the letters mattered. So the tail and head of the vector should be represented with the arrow on it, top of it, right? So my arrow's initial point was at A, and the terminal point was at B, so I'm going to call that AB. If it was the other way around, I'd need to call it BA. Everybody's okay with that? Okay. So what I want is to move this vector without changing its magnitude or direction so that that initial point is at the origin. So I need to be able to do that. Everybody's okay there? That's what I want to be able to do, right? How can we do that? This is just a transformation like we did in geometry, right? What type of transformation are we doing? Okay, so translation, great. How many units are we moving left or right? Okay. Left 3 and up 2. Does everybody agree with that? So our new vector then, A prime, B prime, we got by going from the terminal point, we went left 3, and we went up 2. What do you notice here? We just took the head of our vector and we subtracted the tail of our vector from it, right? Did you guys see that? So we give this a name. We call this the head minus tail rule. I'm going to abbreviate that as HMT. And this says that if I have a tail at x1, y1, and a head at x2, y2, then the component form for that vector is going to be x2 minus x1, y2 minus y1. Okay. Everybody feel okay doing that? That's just what we did before, right? When I did the example, just now we formalized it into a formula. Okay? How do I tell if two vectors are equal? Well, they have the same magnitude and the same direction. So for example, if I have this vector v and this vector u, those look equal to you guys? Probably, right? Looks pretty close. I tried to draw it so they'd be equal. Now, how could we check? What would be the easiest way to check? Ben? Okay, that would work. Is it going to be the easiest way, though? If I take both of these vectors and put them into component form, what are they going to be? They'd be the exact same vector, right? There's no way if I go like over and up the same amount that they'd be anything other than the same vector, right? So one way to check for equal vectors is to put them in component form. And if they have the same component form, then they're the same vector. And what did we have to do to put them in component form? It was really easy, right? We just did that head minus tail thing. Which is going to be a lot less, you're going to see in a bit when we talk about how to find magnitude and direction than finding magnitude and direction. Not that that was wrong, Ben. It would work. You can definitely tell if they're equal from that, but that's maybe not the easiest way to do it. So the formula for magnitude we'll just say 80. So if I have a vector in component form, the magnitude of that vector is Just this. What is this formula really just the same thing as? This is just the distance formula. Right? Remember, our vector is the point 0, 0, and AB. So if I want to find the distance from 0, 0 to AB, I take the square root of A minus 0 squared plus B minus 0 squared, which simplifies down into exactly our formula there, right? So this is just the distance formula. Cool? If our vector was given as an initial point and a terminal point, what can we do? You could either use the distance formula, or you could put your vector in component form and then use this formula. Are you doing the exact same thing? Yeah, they're the same. It's the same thing. Everybody feel okay about that? Okay. Let's talk about finding direction. And let's just do an example. So let's say we want to find the magnitude and direction for a vector v that starts at the point 3, negative 3, and ends at the point negative 5, negative 10. The first thing I'm going to do is take my vector and put it into component form. So I'm going to have end minus beginning, and then end minus beginning. Which gives me the vector negative 8, negative 7. So if I want to calculate the magnitude of v then, it's negative 8 squared plus negative 7 squared, all square rooted. So that's the square root of 113. Now I'm going to draw a picture. So my vector v is down here where this is the point negative 8, negative 7, right? And I'm looking for this direction. Well, I'm going to do just like we did in first semester. I'm going to turn this into a reference triangle. So this reference triangle has side lengths 8 and 7. And I'm going to start by finding this angle that I'm going to refer to as alpha. So because we're working in a right triangle, I can just use SOHCAHTOA. So this is tan inverse of opposite over adjacent. And when I type that into my calculator, I get about 41.19. Everybody's okay there? So I can use that then to calculate the value for theta, which is going to be 180 plus alpha. So 221.19. So from this example, what we've demonstrated is a way to go from a vector in component form and write it as a magnitude and direction, right? That's what this example shows us. How do we go the reverse? This has a little piece of vocab. It's called resolving a vector. It's where we go from magnitude and direction into component form. Well, it's actually quite easy. I just take the magnitude times cosine theta, comma, the sine, or the magnitude times sine theta. Does this look familiar? When you did your vector story problems in first semester, when you added the vectors, what did we do? We broke them down into like a horizontal component and a vertical component, right? How did we do that? We did magnitude times the direction, the angle, the standard measured angle for, sine and cosine. It's exactly this. What we did was we converted the vectors into component form. We added the x components and we added the y components, right? And then we did the process that we just did in the example earlier, where we then found the magnitude and direction of this new vector that we just found and the direction for that new vector. So this is all things that we did in first semester so far. So this last example and then this last formula are the two most important parts from this first section. The ability to go from a magnitude and direction into a component form, and the way to go from component form back to magnitude and direction. We're going to find that frequently when dealing with vectors, we start off with something with magnitude and direction, we turn it into a component form to do some arithmetic, and we turn it back into a magnitude and direction to get our final answer. The reason we do this is that component form is so much easier to manipulate because you don't have to do any geometry. If I'm adding two vectors or multiplying a scalar to a vector or doing any of these other type of calculations and I only have magnitudes and directions, I'm stuck doing a lot of kind of tedious geometry. If I convert the vector into component form, mostly I'm just doing algebra. So things work very, very nicely in component form. Hence, the general strategy throughout this whole chapter is take our problem, turn it into component form, do the problem in component form, take our answer, put it back into the form that we wanted at the end. Next thing up is vector operations. So important, I have to define one special vector That's called the 0 vector. We denote the 0 vector with the 0, and then we have to put the vector hat on top of it. The component form for this vector is 0, 0. The magnitude of the 0 vector is surprisingly 0. And the 0 vector is the only vector that has no direction attached to it. So this is a little bit of an anomalous case. But the number 0 for the real numbers is a bit of an anomalous case, right? What's the multiplicative inverse of 0? It doesn't have one. That's weird, right? What's the reciprocal of 0? Undefined, right? It's like infinity. Ruh-roh. So the 0 vector, again, acts a little bit like the number 0 does, and it's a little weird in the same kind of way. Okay. If I want to talk about vector addition, if vector u is the component form u1, u2, and vector v is the component form v1, v2, then vector u plus vector v is just going to be the sum of the x's and the sum of the y's. So we can call u plus v the sum of the vectors u and v, or sometimes we call it the resultant. Those are both common vocabulary to describe that vector. And this is just like what we did in first semester, right? When like a wind was affecting a plane or something. We resolved both those vectors into component forms, and we added the x component and we added the y components to get our new vector. And then we found the magnitude and direction of that. So this is like algebraically what's going on. If I'm doing this geometrically, if say this is my vector u, and this is my vector v, if I were to want to deal with this geometrically, what I would do is I would take my vector u and then pretend I had a brand new imaginary xy axis at the terminal point of u, and then I would draw my vector v. And then if I attach the origin back to vector v, that's vector u plus vector v. And now if I had to do this all geometrically, to find like the magnitude and direction of this, you're stuck using like laws of sines and cosines, and it gets pretty messy pretty quickly. Not that we can't do it that way, but look at how easy the component form is to deal with, right? What's up in the back there? I can't see. Oh, you're stretching? Okay. Sorry. I couldn't tell who it was. You were squatted down or here, yeah. No biggie. Okay. The next one is the scalar product. Yep. So when I say the word scalar, what does this mean? Just a real number, right? Like 7, a half, square root 4, pi, whatever. Any real number is a scalar. So in this case, I'm going to use the letter K to be my scalar. And my vector U is going to be U1, U2. K times vector U is just K times U. K times U1, and then K times U2. So again, this is like my algebraic description. What does the geometric description look like? So if this is vector U, this would be like 3U. Right? We're just kind of doing it as you would imagine vector addition. So like U plus U plus U is 3U. Everybody okay there? I'm sorry, what?
Mr. Blue, on the graph, are those both like vector signs will have things over the news on both of them, or is one alone? You know what I'm saying, like in red?
Yeah. Yeah, they're all vectors. The 3 isn't a vector, but you know what I mean.
Yeah.
All right, so let's say I have the vector U and the vector V. And I want to do 5V plus negative 3U. Well, I'm just going to start by replacing my vectors with their component form. And then which order would I want to do things? Should I do the scalar multiplication first, or I should do the vector addition first? Same as the order of operations that you've done previously. So we should do the multiplication first. So there's that. And there's that. What do you guys think? Pretty easy, right? That's the beauty of working with things in component form, is it's just the algebraic, right? Everything works kind of as we'd hope it would. Okay. So if I want a vector additive inverse, so let's think back to what I mean by additive inverse. What's the additive inverse of 5? Just back to real numbers. This is like 3rd grade. -5. Thanks, Anne. So what do you think's going to... And why is -5 the additive inverse of 5? Because they get 0 when we add them together. Excellent. So what's going to be the vector additive inverse for some vector v? That's v1, v2. So the additive inverse for vector v we're going to denote as negative v, which is negative 1, or I'm sorry, negative v1, comma, negative v2. Works exactly as you'd hope it would, right? Why is this going to work as a vector additive inverse? When I add the two component forms together, what do I get? 0, 0, which is the 0 vector, right? So it works exactly like we'd hope. Why is this important? It allows us to define vector subtraction. Oops. So vector subtraction works exactly what you'd hope it would be, or how you'd hope it would work, right? Very simple. Agreed. This is good, though, right? We want it to work exactly as we'd expect. We don't want some weirdo addition that, like, oh, you have to, like, you do this, and then you do that, and then you have to do this. And no, we want it to work as we'd expect it to work, right? Okay. Next thing we want to do is define a special kind of vector called a unit vector. So we say a vector u is a unit vector if and only if the magnitude of u is 1. So if I wanted to describe the set of all unit vectors of the form, I should say, in component form, how would I describe that set? All of you should know this. What do you know that's related to directions? That everything has length 1. Think back to first semester. You probably use this every single chapter of first semester. The unit circle. The unit circle has length, all the radii are 1, right? And any point on that perimeter of the unit circle corresponds to some standard position angle, right? So the component form for all unit vectors is going to be cosine theta, comma, sine theta, where theta is some angle between 0 and 360. Whoa! So the beauty here is essentially what you're able to do is just describe a direction for the vector with a unit vector, right? the magnitude is kind of negligible with 1. Particularly when we start doing some of the more complicated things a little bit later. The unit vectors become very important. So how do I transform well, let's see. Shouldn't say transform. How do I get the unit vector in the same direction as some vector v? So v is not a unit vector, but I want to be able to write down another unit vector in the same direction. What can I do to v to give me that unit vector in the same direction as v? I'm going to just denote this unit vector as the vector u. How do I find u? What's going to be the easiest way to figure out u? Has to have the same direction as v, but it needs to have a magnitude of 1, right? So what if I just multiplied vector v by some scalar that creates a magnitude of 1, right? Multiplying by a scalar isn't going to change direction. It's just going to stretch or shrink that arrow, right? So what should I multiply vector v by? When I write it down, you guys are all going to go, oh, I should have guessed that. 1 over the magnitude of v. Right? If v is length 5, if I multiply it by 1 over 5, it's now a unit vector, right? And it's still in the same direction as v. Oh, yeah, sure, of course, right? Like it's super obvious now that we say it, but to come up with it on your own, you know, maybe not. So let's say here that v, just to do a numeric example, just so we're all on the same page here. Let's say v is the vector 5, negative 6. What's u going to look like? Well, I'm going to need to know the magnitude of v. So that's going to be 25 plus 36 for the square root of 61, right? Everybody's good there? So u should be 5 over square root 61, negative 6 over square root 61. Who likes the way that answer looks? All of you guys should say no, I don't like that. What's wrong with it?
Radicals on the bottom.
Yeah, so we really want this 5 square root 61 over 61, negative 6 square root 61 over 61. And that's what we really want that to look like. So we have two special unit vectors called the standard unit vectors. One of them we call vector I, which is the vector 1, 0. And the other one we call vector J, which is the vector 0, 1. So what's lovely about the unit vectors is it allows us to rewrite any vector as the sum of two vectors very easily, specifically the sum of these two unit vectors. So for example, if I have the vector 3, negative 4, I can rewrite this as 3, 0 plus 0, negative 4. Anybody agree with that? That should be obvious, right? Goes without saying. Now the vector 3, 0 is really the same thing as 3 times the vector 0, 1, right? And 0, negative 4 is the same as the vector negative 4 times 0, 1. So that's 3 times vector I minus 4 times vector J. Right? And I could do this for any vector v, right? I can resolve that vector into a combination of vector I and vector J. In fact, we have a special name for this. This is called a linear combination. And when I write my vector as the sum or difference of unit vectors, we call this the linear combination form for a vector. Right now, is this helpful to us? Not right now. Will it be helpful later on in this chapter? Yeah. It will. Are we done here? Do you want to talk about dot products?
No, I don't even know what.
Yeah, that's probably a good place to stop then. That's a healthy size